Alrighty, so here's part 3, or the third video in our series. So I want to show you one involving springs. Okay, so we've got a spring here. You can see there's a little finger pushing on it, and the original length of the spring was 75 centimeters, and then it's been pushed back to half a meter, back to 50 centimeters. All right. Now, when we're dealing with springs and forces from springs, okay, we use this equation right here. Okay, so let me kind of show you how this works. Our delta x is always defined anytime you have a delta. Remember, it's going to be it's ending minus beginning. So that means we've got 0.5. It's where we started, it's where we finished. Delta is always finish minus initial, minus 0.75. So 0.25 is what we got. So it's 25 centimeters smaller. Okay, just like that. Now then, if we put that into our equation, what we're going to have is minus 600 times minus 0.25. And you can see then the minus times the minus cancels, and we're left with 150, and that's 150 newtons this way. Okay. So what does that mean? Well, a spring is a restoring force. You see, there is a direction with our delta. Our delta x is negative, which in this case means it's to the left. All right. And so what we're doing in our spring equation is we're saying we're going to go the opposite direction of whatever our delta x is. And so if our delta x is to the left, the spring ends up pushing to the right. If our delta x is to the right, then the spring ends up pushing to the left. Okay, so instead of pushing on this spring, if it had been something that's trying to pull it out, pulling it out would have given us a positive delta x, which would have meant that overall force then was negative, meaning it's going in the opposite direction like that. Okay, now that's an idea that we're going to come to in the future, but I just want to put it in your head for now, is the idea that what we have in a spring is something called a linear restoring force. Okay, so it's linear because it's not x squared or x cubed or the square root of x or anything like that. It depends straight on x. All right, and it's restoring because that means whichever way you push it, it tries to go back. Push it one way, it goes this way. Push it this way, it goes back way. So that's what we call a restoring type force. Okay. And all right, let's look at another spring example. So we're going to take the same spring and I'm going to attach it to a block here. All right, and there's going to be some friction acting on this block. And what we're going to do is we are interested in how much, if we push on the spring, how much does the spring compress before the block suddenly gives. Okay, like that. So you can sort of imagine if I had my block, and then my spring is going to coil, and then at some point I'm going to be able to move the whole thing. All right, so that's what we want to know. How much are we going to have to compress this thing to get that to happen? Okay, so we've got our force that we're applying here. We call that capital F. And then we're going to have, I need a better color, we're going to have a normal force here. And we're going to have the weight down here just like this. Okay, transfer everything over to our free body diagram. And we've got the force that's acting, our push. Friction is holding it back, and that's static friction. S is our hard. Okay, and our normal force, and then our weight. Okay. And you can see what's going to happen here is that our normal force and our weight are equal and opposite. Okay, so a nice case where we've got a simple normal force. And then our force that we're pushing is going to have to try to match the maximum that the static friction can provide. Okay. And so we have F to the left plus our static friction there. Okay, so F is just going to be, whoops, our static friction. Okay, and normally then we would say less than or equal to mu S times the normal force. But in this case, since we're interested in the maximum, we're going to go ahead and set it equal mu S times the normal force. And our normal force is the weight, so we have mu S mg, just like that. Okay? Okay, so that's how we relate the force from the finger to the friction of the block. Okay, so the spring is inside there then. The spring is inside there. So what we could do is we could say, well, if we look at the block without the spring, all right, the spring is going to be compressed and the spring is going to be pushing on the block. So we could say here, I've got a force from the spring, just like this. Okay, and that means we could come through here and say that this is our force from our spring. Okay, now I have a new set of relationships where we can say mu S mg has to be K delta X. Okay, now you see I left out the minus sign there, and that's probably going to bug some of you. You need to start thinking about plus and minus as direction. Okay, as direction. And so because of that, a lot of times, most of the time, in fact, we're going to end up, when we talk about the force from a spring, we're going to end up talking about the magnitude of its force. Okay, because we will have already derived direction from our diagram. So we'll already know if the spring is pushing left or up or down or wherever. Okay, and so then all we really need is the magnitude of the thing. And that's what I'm doing here. Okay, so do a little bit of algebra here. So delta X, we're going to end up getting mu S mg over K. Okay. And if you plug in your numbers on this guy, what you get is 0.196. Okay, so almost 20 centimeters. Okay, almost 20 centimeters. Now, what we would see if we pushed in on this thing like that is the friction can match what we're doing right up until that point. Okay, when we go 1 millimeter further, now our spring is pushing more than the static friction can bear. And then the bond between the surfaces becomes weaker and the thing will start to slide and we'll be in a kinetic friction scenario. And so you'll see it'll pop forward just like that. Okay. You see this kind of thing all the time. Like if you're pushing something like maybe you've got a pink eraser or something, you might try this really quick. If you got one of those pink erasers or something with a rubbery bottom on it, okay, and you sort of push, and what you'll notice is it kind of jerks while it goes. It can be hard to push it smoothly if it's got a little bit of a little rubber feet on it, and it kind of goes, it sort of jerks along like that. And the reason for that is because we have the same thing. You push it, and the rubber bits stretch. And then it's too much. There's too much stress on them. And then we lose our static friction and becomes kinetic. And then it slides until it stops. And now it's static again, which means we got to push it and stretch the little rubber bits till eventually they can't do it anymore. And we lose our friction and it slides again. Okay. Anyway, just kind of play. You can play around with that, kind of get an idea how those things work. Okay. All right, so one more thing we're going to look at here in part 3, and that is pulleys. Okay, so let's suppose we have this 120 kilogram block, and here's some different pulleys pulling on it. Let's start with A here. So A, we're going to have the 120 G, because A is the mass, right? M is the mass. The mass is 120, so the weight's going to be mg, so 120 G. That's our weight. So if the block is in equilibrium, then pulling up, we're going to need 120 G. All right, just like that. Okay, piece of cake. I mean, and then it's kind of like, well, what's the point? Well, I suppose if it's easier to do this, maybe that's the point. Let's look at B, though. B is a little more interesting. B, it's still, we have something pulling down, but now with B, we've got 2 lines pulling up. Okay, each of those lines has the same tension in it, because remember, we're using a simplified model. We're going to assume the tension doesn't, or the pulley doesn't interfere. All right, and so that means we've got 2 of those guys right there. So that means we got 2 tension, has to be 120 G. So each one is half. Okay, each one is half. So if we did it in pounds, if it's a 300-pound block, then now I only have to pull with 150 pounds. Okay, so that works out pretty good. In C, we've got the same kind of thing. We're going to have 2 tensions here. And so, again, our tension is going to be half of the weight. But what C does for us that's pretty nice is it allows us to pull downward. Okay, and it's just easier for people to pull down. Plus, then your weight actually aids you. Okay, like that. So there's a lot of good physiological reasons for pulling on it. That works well for human shapes. Okay, D is kind of odd, but look at D. D here we got 1, 2, 3. Okay, now pulling that way would be difficult. Okay, and you wouldn't want to have to pull very much, but you could see then we've got 3 tensions, and so that means it's going to be cut, the weight will be cut in a third. Okay, so we do a lot less that way. Looking at E there, same sort of thing in the sense that it's cut into 3 pieces, 1, 2, 3. But again, we get this nice physiological help there because we're going to be pulling down. Just like that. Okay, so anyway, pulleys are kind of fun, and they're usually pretty straightforward to analyze once you kind of get the trick of how to do them like that. Okay, now the downside on a pulley is you end up having to pull twice as much. Okay, and we'll talk about that another time, but take a look there at C. All right, so if I pull 2 feet, all right, I pull 2 feet of rope. That 2 feet is distributed around the lower pulley. So each one of those is only going to move a foot. So I pull 2 feet, it only moves a foot. So I have to pull twice as much rope. Okay. Get to D and E, I have to move 3 times as much rope. All right. Okay, there we go. That's part 3. We got one more to go in this series.